Welcome to lecture number 6 of CIVE 360. Normally in a regular classroom, what we typically try to do at least once a week is to have something of a drill practice review session. And we do that by very quickly trying to answer these questions off of the top of your head. I pose questions. I ask the class to pause for maybe 2 or 3 seconds, and then I have them answer together. And what that does is it kind of lets you know where you stand, especially with the rest of the class, if you're keeping up or not keeping up. And I'd like to do that right now, so I don't want you to press pause on any of this. I want you to go through it and answer these things just like you would normally. And then I will pose the question verbally. I'll give you a couple seconds, the same sort of time frame that I would do in class, and then I'll write down the answer and you can see if you got it right or not. And what I typically do again in class is to do these on Fridays because it's kind of the end of the week and it lets you know where you're doing. But you'll be watching these at different times. So what I'll try to do is I'll basically take lectures that are divisible by 3. Now I didn't do it on lecture number 3. Lecture number 3 divided by 3 is the first time because we hadn't done all that much and some of it was administrative. So we'll try to stick with this for the rest of the semester, the rest of the class, so that you've got some practice sessions going through. All right, so let's go ahead and start. So the first question, and again, I normally repeat these so that you've got some time to mentally process. First question, what is a symbol for normal stress? Symbol for normal stress, the answer is sigma. What are the dimensions of normal stress? The dimensions of normal stress, those are force per length squared. What is the symbol for shear stress? The symbol for shear stress is tau. What are the dimensions of shear stress? The dimensions of shear stress are force per length squared. What is the symbol that we use for the normal strain? Symbol for normal strain is epsilon. The dimensions of normal strain. The dimensions of normal strain are, you can either say length per length, or you could say dimensionless. I'm just going to write it as dimless. What are the dimensions? What is the symbol for the shear strain? The symbol for shear strain is gamma. What are the dimensions of shear strain? The dimensions of shear strain, you can either say length per length, you can say radians, or you could say dimensionless. This one is a little bit better, as I've said before, earlier on in the class. I start with 2 lines that were originally like this. They get bigger. Is that a positive or a negative shear strain? 2 lines that were originally perpendicular, they get bigger than 90 degrees. Is that a positive or negative shear strain? It's negative. So we've got that mnemonic. That was your first time to practice it. Hopefully you got it right. There was a line element that is this long. After deformation, it increases in length. What is the sign of the normal strain? The sign of that normal strain is positive. What is the symbol that we use for the modulus of elasticity? The symbol for modulus of elasticity is E, capital E. What are the dimensions of the modulus of elasticity? The dimensions of modulus of elasticity, force per length squared. What is the symbol for the Poisson ratio? The symbol for the Poisson ratio is nu. What are the dimensions of the Poisson ratio? The dimensions of the Poisson ratio, none. Now you could say length per length over length per length. What a waste of talking. So it's better to say it's dimensionless. Remember, it's a ratio of strains. What is the symbol that we use for the shear modulus? The symbol for shear modulus is G. What are the dimensions of the shear modulus? Dimensions of the shear modulus, force per length squared. Finally, last question for our first go. How many independent components of stress are there? The number of independent components of stress, 6. All right, so you can do a little assessment for yourself. Ask yourself, how many did I get? If you got 0, no offense, but you stink. You got to do a little bit harder work. If you got them all, that's fantastic. If you got half to 2/3, that's not bad, but you should probably work a little bit harder. And again, the best way to do this is to create some sort of sticky note. Especially since most of you taking this online, you're not going to have some sort of peer support system that some of our students in class might have. And so it really helps to kind of talk to yourself and have these symbols sitting there in front of you and rep them a few times a week, if not every day. And so you get a little bit better at that. Now, where are we in this class? This is another thing that we could certainly test, but we've got this hierarchy: displacement to strain, to stress, to force. And we've done that for a couple of types of solids when we made the constitutive link. But now what we get to do is actually apply this to our first real problem. And we will call this the axial bar. Maybe we'll say the axially loaded bar displacements. So even though we had an example last time, that shear block example when we went from start to finish, this is an even better one. And it looks like this. We've got a axi bar. So again, you can think of it as being, a pencil or a 2x4 or a piece of rebar that's loaded along its long direction. So it's got some sort of P right there. And as we said earlier, when we do that, it deforms. Now you can either write that as U, but U is a generic symbol that we're using. So for the axial bar, it's more common to write it as delta, and that is equal to the axial displacement. And the axial displacement, remember, we get by integrating the strain. So what that means is that we have this expression. We have epsilon, which is du dx. So this is the axial displacement at the end. U then, in this case, represents the generic axial displacement. So it's almost like we have a variable that we're using, but then at one location, we're just going to use another symbol to represent that. So the delta is kind of traditional to use as some value that we've got at an endpoint, whereas U is kind of, a little bit more of a generic symbol. So U is equal to U of x, and that means the axial displacement at any x. So we could really say that U at L was equal to delta. That's just one symbol that we're going to be using. And again, L is the length of our bar, like so. All right, so that is the symbol that we've got. And we also know then that strain for the axial bar, it's a one-dimensional problem. So we've got that is going to be sigma divided by E. So the strain is the stress divided by the modulus of elasticity. So there's our constitutive law. Remember, this is a kinematic relationship. We differentiate displacement to get the strain. Then this relationship between strain and stress is linear, and it's quantified by the parameter E. But then we also know that sigma is P over A. So we have P over A, and then the E was sitting there originally. So notice what happens. That means that strain at any point in the bar is the axial force divided by the area divided by the modulus of elasticity. So that can either be uniform or it can vary. So we will say can vary with X. So for example, our bar that we had earlier with aluminum and silly putty, even if it had the same value of the force and the same area, the modulus of elasticity would have been different. So now we can write du dx is equal to, again, epsilon, which is P over AE. But now what we want to do is multiply through by dx. So we have a du, in other words, the change in the axial displacement as we move down. So the change in displacement is equal to P divided by AE multiplied by dx. So of course, the way that we sum all those up over a distance of the bar is to integrate. So we're going to sum up all the little du's. And so we have du. Now remember, the limits of integration we have to put on our variable of integration. So that would be from some location 2, some displacement 2, and some displacement 1. And then we have the integral of P over AE dx. So we have to put limits on the variable x. Normally, we would do that over the entire length of the bar. It could be an x2 and an x1. In fact, let's do that as a generic x2 and x1. So what that means is we've got, let's sketch in maybe our coordinate system. There is x. There's a length of bar. It might start at the origin, it might not. But this would be our x1. This location would be our x2. This value would be the u at point 1, the axial displacement at 1. This would be the axial displacement at 2. So the generic form then, if we did this, we integrate and substitute in, we would have u2 minus u1. That's the change in displacement between locations 1 and 2. So that's our 1. That's our 2. So 1 and 2 indicate locations along the bar. And that's simply going to be, we can't do much else about this one. It's going to be integral between those two spatial points of P over AE dx. Now, that one, that expression is fine, but almost always we want to do for the entire bar. So most times are, if we've got a bar that looks like this, that is our point 1, that is our point 2. And the left-hand end of the bar doesn't move, so the u at 1 is equal to 0. And the u at 2 is equal to delta. So what that means is, and incidentally, it also means that x1 is 0 and x2 is equal to L. So almost always we would write it as delta is equal to the integral from 0 to L of P over AE dx. And that one we want to commit to memory. We get the end displacement by integrating the strain over the length of the bar. So that goes on the sticky note also. And that also ends the first part of today's lecture.